All right, we're taking a look at day 8, which is circles here today. So we're going to take a look at the first part of our circle. Remember, the different parts of the circle are formed by the different line segments for the angles and the segment lengths. So remember, a tangent line is a line that touches the circle at only one point. A secant line is a line that cuts through the circle more than twice and extends beyond the circle. A chord is a line segment inside the circle that touches 2 points on the circle. The diameter really is like the longest chord you can have. And we also know that, remember, half the diameter is referred to as the radius, all right? So, types of angles that are formed inside the circle. The number one is the central angle, okay? So the central angle is formed at the center of the circle, and the key thing here is we're going to talk about the central angle is the same. Now, that means the vertex is at the center, so keep that in mind. The vertex is at the center, it's the same. If you have an inscribed angle, which the vertex is on the circle, we always think of half. And another type of angle that we can think of that is created from a circle would be, all right, one formed by a tangent line and a chord. Now, if I have a line that's drawn tangent to the circle, okay, and a chord, this angle that's being formed here is also considered to be a type of like inscribed angle, at least. It's on the circle, and it's going to be half of this intercepted arc here that we have, okay? So if it's on the circle, it's half, all right? Now, if it's inside the circle, it's going to be the average. So if the vertex is located inside, like it is here, we're going to do the average of the two arcs, the intercepted arcs, okay? So if we're looking at angle AOD, we're going to use arcs AD and BC. And if we're using angle AOB, we're going to use these two arcs, AB and DC. So it's always the arcs creating that angle. And then if the angles are outside the circle, remember, outside is different. So we're going to subtract, and we're going to do big arc minus small arc, okay? So we can see over here that the big arc is AD, the small arc is AC. The big arc here is IH, and the small is EG. The big arc would be KML, and the small arc would be KL. So it's 1/2 the big minus the small. All right? Okay, number 149, which is next on the next page. We have circle A below, and the important parts here, we have a chord BC, diameter DAE, which intersects at F. We have CD, which is 46, DB is 102, and what is the measure of angle CFE? So first thing we're going to want to do is label our information. So we have 46, okay, DB is 102, and we're trying to find the measure of angle CFE. So remember, this angle is inside the circle. The vertex is inside, and inside, remember, is the average of the arcs. Now, because the angle is here, the two arcs we're using is DB and CE here. So the first thing we need to do is figure out the measure of this arc. And since this is a diameter here, we can just do 180 minus 46 to get it, which is 134. And then since we're doing the average, we're going to average the two arcs. So 102 plus 134 divided by 2 is going to be 236. And then when we take half of that, we're going to get 118. So that is the measure of angle CFE. All right, let's take a look at 151. Now in 151, we have circle O. We have the points KATI, which are going around the circle. The two triangles are given as KAE and ITE. We know that this arc KE, which is down here, is equal to EI. And we know that angle EKA is equal to angle EIT. So this angle is the same as this angle. Now remember, we already also noticed that these angles are on the circle. So remember, angles on the circle are half, okay? So this angle is going to be half of this arc, and this angle is going to be half of this arc. And since the arcs are congruent, these angles are going to be forced to also be equal. That means that we'll know that these two triangles, right, are going to be similar, at least, because it has angle. Now, another key thing to think about here, okay, is that remember that congruent chords, okay, or I should say congruent arcs form congruent chords. So since these two arcs are equal, these two chords are also going to be the same. So we had angle, angle to make the triangle similar, and now we just threw in a side length congruent. So now we have angle, angle, side. So if we go through the choices, which is always true, that they're neither congruent or similar is out. They're similar but not congruent now is out. We don't know the right triangles. In fact, we know they're not because these angles are not formed by a diameter. So they're more than half the circle. So these two angles have to be more than 90, and instead we're going to choose choice 4. Let's take a look at the next one. All right, in 155, we have diameter AC, we have a chord AB, we have radii, okay, MB drawn. All right, and also keep in mind that AM is also a radius, and so is MC. So which statement is not true? Now, since this angle is inscribed, and the arc being formed is exactly half the circle, which is 180 degrees, and the vertex is on the circle, it's going to be half of that, so this is going to be a right angle. So this is true, and since we're looking for not true, we're going to say that's false, okay? Or sorry, that we're not going to accept it because it's true. Now, the other next one we're looking at is triangle ABM, which is right here. And we want to know, is this isosceles? And remember, since these two lines are radii, they are going to be equal. And I don't know the length of this one, so I don't know that it's equilateral. So this is true, so we're not going to accept that one. All right. For number 3, triangle BMC, which is located right here. All right. Or angle BMC, I should say. So let's get rid of this guy. Just this angle is a central angle. And remember that it is the same as the arc. So the arc equal to the angle is also true, which means our correct choice is going to be choice number 4 because, okay, angle ACB, which is this angle right here, okay, is on the circle, and it's supposed to be half of the arc. But it says that it's half the angle. So the half should be over here. Or, instead of this being half, this should be times 2 instead of a half. So that is going to be our answer. Let's take a look at next door at number 159. Now we have a quadrilateral inscribed in a circle. So just like above, we talked about the bottom of the page here, that remember the opposite angles add to 180 degrees. Okay, so we know that angle F is going to add to 180, okay, with the angle that's 86. So 180 minus 86 is going to equal angle F. And so angle F is going to equal 94 degrees. Now, the second part is, what is the measure of angle arc GFE? So arc GFE is all the way over here. And since this angle is on the circle, it's half of the arc. So we're going to double the angle to get the arc. So the measure of GFE, arc GFE, is going to equal 172 degrees. Let's take a look at the next one. All right, so in 158, we have the picture shown below. We have 2 secant lines being drawn here, okay, from a circle O, which is the center. Point P is located outside the circle. Angle RPS is 35. Arc RS is 121, which is out here. And WT is the arc that's inside here where the intersection occurs. Now, because the angle is outside, we got to remember that we're doing outside is different. So we're going to subtract and do big arc minus small arc over 2. So if we plug into the formula, we're going to get 121 minus x over 2 is equal to 35. And then to solve from here, we can cross multiply. So we get 121 minus x is equal to 70. When we subtract this 121 from both sides, we will get a negative, but remember the x is negative. So the answer here is just going to be 51. All right. Keep in mind, though, if we're really asking ourselves what minus 121 or take away from 121 is going to give us 70. So that's why 51 should make the most sense. All right, on to the next page. Okay, so the lengths of the parts of the circle. So we're talking about segment length. Remember that anytime we see a secant line, we're going to think of the whole times the outside. okay, whole times outside. And anytime we see the tangent line, we're going to think of tangent squared. All right? So if we have a tangent line, we're thinking tangent squared. And we see the secant line, we're doing whole times outside. So if we have two secant lines, we're going to be doing whole times outside for both of those lines. All right? And then if we have angles that are intersecting in the circle, okay, inside the circle, we're going to multiply the parts of those two chords together. So AE times ED here, AE times ED, okay, is going to equal the parts from the other two chords, which is going to be CE and EB. So just part times part for each chord. All right, let's take a look at 141. All right, number 141, we have the figure below. Oh, geez, we're erasing stuff already. Okay, which is this quadrilateral that's circumscribed, so the circle's inside of it, which basically means that we are getting what's called the hat rule. So remember, in the hat rule, if the two tangent lines are outside the circle from the same point, those two tangent lines are equal. So tangent line is equal to a tangent line. And if we connect a radius out, which happens on some questions, it's going to form a right angle. Now, in 141, we know a few things. Number one, we know that R is the midpoint of TA, so to get there. And we know HO is congruent to PE. We know AP is 10, EO is 12, and we are trying to find the perimeter of that quadrilateral. So, key thing, because of the hat rule, we are going to know that these two lines, PE and EZ are equal, and HO and OZ are equal. Since HO is equal to PE, that is going to force these four lines on the bottom to actually be the same length. And then on the top, we're going to know that AP and AR are equal, and TR and TH are equal. And since R is the midpoint here, and RT and AR are equal, these four lines on the top are the same. So if AP is 10, that means all the lines on the top here are 10. And if EO is 12, that means that these two are both 6. So all of these are 6 on the bottom. And since we're looking for the perimeter, we're just going to do 4 times 10 plus 4 times 6, which is going to be 64. All right, let's take a look at 144. Okay, in 144, we don't have a picture, so we're going to want to draw that first. So remember, we're going to do secant lines. So we should be thinking of whole times outside. Okay, whole times outside. All right. So when we're doing this question, we want to draw the secant lines, which are AB and AC. Okay. And then if AD is 8, AE is 6, EC is 12 more than BD, we want to find the length of BD. So key thing here. All right, we're going to, after we draw the picture, two secant lines, because they're coming from the same point outside the circle. So let's draw this together just so it's a little bit easier to do. Okay, so what we're going to do is draw ourselves a circle. Now, because A is the same letter in both secant lines, I know that A has to be outside the circle here. Okay, and it's going to be drawn something like this. All right, now it goes from A to D to B, and then A to E to C. So that's how it looks. And circle is O, so O is the center. So if, okay, AD is 8, and AE is 6, not drawn to scale, EC is 12 more than BD. That means I need to know BD first. So I'm going to call that X. So then this line is going to be X plus 12. Okay, so when we do whole times outside, we need to know what the whole length is, and we add that together. So X plus 8 for the whole, and this line is X plus 6 plus 12, right? X plus 12 plus 6, which is really just X plus 18. So the whole line on the top is X plus 8 times the outside piece, which is X, is equal to the whole line on the bottom, which is 8, or sorry, not X. The outside piece is 8. The whole line on the bottom is X plus 18, and the outside piece is 6. So we're just going to distribute through to solve. So 8X plus 64 is equal to 6X plus, and then 6 times 18 is 108. Okay, we can move the 6x to both sides here to solve. So that's going to be 2x plus, well, we can actually also move the 64 back to the other side and do this in one step, is going to equal, and then this doesn't go away, 44, and then divide by 2 to get the value of x. I can't say this enough. Make sure you reread the question before you circle an answer. Because if it had said AD, and you circled 22 because that was x, you'd get this wrong. So make sure you go back and double check, okay? But the answer should be choice 2 because we called BDX, and that's what we found. All right, let's try the next one. All right, so for 146, we have, in the diagram shown below, PA is tangent to the circle. We have a secant line being drawn. So remember, whenever we see tangent in a secant, we're going to think to ourselves, tangent squared equals whole times outside. So we're going to label our sides. So PB is going to be 3, PA is 15, and then we're looking for PA, which remember is x. We're thinking tangent squared. And remember, we need to do whole times outside, so the whole line is going to be 18. All right, we're going to plug into our formula. So whole 18 times outside of 3 is equal to x squared. 18 times 3 is 54. We're going to take the square root of both sides from there. And then remember that on your calculator here, okay, we can do our, we're just going to do new document. Grab a calculator page, menu, number, so 2, 3. And then if you type in your number, it'll break down that into prime factors for you. Okay, so it should be 3, 3, 3, and 2. We're going to circle our pair of 3s to bring it out and get 3 square root of 6 as your answer. Now, if we know the answer is also the square root of 54, if we type that into the calculator, we can just match the answers, okay, to that, and we can check to see, like we did here, if I do 3 square root of 6, I should get the same decimal. And if I do, then I know that these are equivalent answers, and that's the one I want to pick. So you can always check your answers when you're done. And also, since the square root of 54 is not 9 or 3, we would know that that one has to also be out as well. All right, 147 is next. Okay, so for 147, we have PS, which is tangent to the circle. PQR is a secant line. And then we have our segments. So PS is x, PQ is 3, and PR is 18, x plus 18. The question here, should be defined PS, okay? So we are going to, remember, ignore any parts that are past the circle. So we're going to ignore this segment and this part here. And then remember that whenever you see a tangent line and a secant line, when we're looking for segments, it's going to be tangent squared is equal to the whole times the outside. So we take a look at this one. Remember, the outside piece is PQ, the tangent line is PS, and the whole segment is this x plus 18. So 3 is outside, PQ is x plus 18, okay? And then PS is x, and that's the tangent squared. So plugging into the formula, we should get x squared is equal to x plus 18 whole times the outside, which is 3. We're going to distribute through to get x squared is equal to 3x plus 54. And because we notice that has an x squared as a quadratic, we want to get everything equal to 0 and keep the x squared positive. So we're going to move the 3x and the 54 to the other side, which gets us x squared minus 3x minus 54 is equal to 0. Now from here, remember, if we think about factoring, we want numbers that multiply to negative 54 that also add or subtract to give us 3. So multiplying to 54 to 3 would be 9 and 6. And since we want a negative 3, the 9 is going to be negative. So our factored form is going to be x minus 9 times x plus 6. All right. And then remember, you're going to set each of these equal to 0. So what do I need to plug in to make this turn into 0? That would be 9. And what do I need to plug in to make x plus 6 turn to 0, which would be negative 6? Okay, so keep that in mind here, all right, as we're working along, and it's an or. Now, because we're talking about segment lengths, we can't have a negative 6 as an answer, so we know the answer is going to be 9 because we're looking for a PS, and that's what we called x. All right, the last one on this page is next. All right, number 148. So in the diagram below, P, Q, and RS are on the circle, which relationship must always be true? Since we're talking about the segment lengths here, there's no angles in the answer. We know that we're inside the circle, and we're going to multiply the parts of these chords together. Now, the answer doesn't necessarily mean it's the product. It could be a ratio, but we don't see any ratios here. So as long as we take the parts from the same chords, so RT times TS, okay, that has to equal the parts on the other side, which would be PT and TQ. So that's why choice 4 would be the correct answer. However, okay, the reason why we don't know that these are equal to each other is because I don't know where T is located. Okay, we can kind of slide our points around and change where T is. So that's why these aren't going to be the same. And it's not adding, it's always multiplying the segments. Now, what I could do to get a different answer is I could, for instance, let's say, move this TS to the other side, right, over here by dividing, okay, and then bring the TQ back by dividing. And maybe I might something like RT over TQ is equal to PT over TS. So if they want to get tricky, they could make a ratio out of this. But I probably would not see that most likely. It's going to be something that looks similar to what we have here. Okay? All right. On the next page, we've got a few more statements. Remember, if we have parallel chords, like a sandwich, the arcs are going to be equal. If inscribed angles here share the same arc, they have to be equal. Remember that congruent chords have congruent arcs as well. All right. And then in number 147, we're going to take a look at that one next. Okay. So since we have the chord, which is parallel to the diameter AOB, and CD is 130, we want to find the length of AC. Now, since the chord and the diameter are parallel, that means AC and DB are going to be equal. So if we know that CD, that whole arc, is 130, and A to B all the way around the top here is half a circle is going to be 180, then if we try to figure out what AC is, DB is the same thing. So really, we can ideally think we're going to take 180, take away 130, and then just divide by 2. So that's going to be 50 over 2, which is 25. And our answer is going to be number 1. All right, number 142 is next. If we look at number 142, we're going to notice a few things here. All right, number 1, we have these lengths of 4 and 5, okay, in our triangles. And we know that AC is tangent to the circle at O, at A. So if we have a tangent line meeting a radius, that is going to form a right angle. And if it's also tangent to circle P at C, and we have a radius and a tangent line meeting, that is also going to form a right angle. So if OA is 4 and AB is 5, we want to find the length of BC. We're really looking at these two triangles. And since we have vertical angles here, we know that these two triangles are going to be similar. And anytime we're looking for side lengths in a triangle, when they're similar, we can just make a proportion. Now, if you look at this, you'll notice that this triangle is bigger than this one. And if this is 4 and this is 5, if this is 10, this obviously needs to be bigger than 10 because it kind of corresponds to the 5 here. So we could rule out these two answers right from the beginning. We know it's got to be either 3 or 4. So you could probably guess what the answer is just from that. Now, if we do make a ratio and we compare the corresponding side of 4, right, which corresponds to the 10, and make a ratio using the 5, which corresponds to x, we can cross multiply and solve here. And so when we cross multiply, we're going to get 5 times 10, which is 50, is equal to 4 times x, which is 4x. And then when we just divide out by 4, we're going to get x is equal to 12.5. And so that is going to be our answer. Highlighter. All right. Take a look at the next one. Okay, so in the diagram below, we have circle O. We also have a radius of 5. Now that means that any radii we draw, including CE, has to also be 5. So kind of neat how we think about that. We have a diameter at AC, which is perpendicular to BD. And remember, if the diameter is perpendicular to chord, it also is going to bisect it. So if we're looking for the length of BD, the first thing we want to do is kind of look and see that, hey, we got this right triangle going on here. Remember that this is a radius, so if the length of that is 5, that means that EO has to be 3. And if we focus on this triangle here, we're really going to use Pythagorean Theorem. So we can okay, look at this and say, all right, if this is my B and this is A and this is C, we can use our old C squared minus B squared formula. These are solve. So if we're plugging in, okay, we do 5 squared minus 3 squared is equal to A squared. This is 25 minus 9, which is going to be 16. And then we take the square root of this to get the answer. Now, if you chose 4, you would be wrong. Because remember, it says to find the length of BD. And since this is cutting it in half, each of these is 4. That means the answer is going to be 8. Okay, just a little bit left here to finish up.